For the second example, you measure time from surgery until discharge from hospital. So time from surgery until discharge is the time variable, and the event of interest in this case is discharge from hospital. For the third example, you measure time from successful cancer therapy until remission ends. So you have a period where you measure time, and the end of the event of interest in this case is remission, or the end of remission, or the patient relapse, and so on. And the response or the outcome variable is often referred to as event time. In this case, you measure time until a certain event of interest occurs, and this is your outcome variable. So you have two information which you measure. The first information is concerning the time where subjects are observed, and the second response or second thing what you measure is if the event of interest occurred or not. So you have two information in time to event analysis which you measure or observe. But what is special to time to event data? Let me explain it via this diagram. Here for illustration I consider a hypothetical study consisting of 1 year recruitment period and a follow-up period of 2 years. So we have a study of 3 years duration. In the first year, patient went into the study, and after the recruitment period, patient were followed up for 2 years again. The first patient went into the study at the beginning of the study, and then were followed up until the beginning of the year 2005. The second patient went into the study in the first quarter of the year 2004 and were observed until the end of 2005 and so on. The third patient were recruited into the study at the beginning of the study and then were followed up or observed until the end of the study. And here you see that for some patient, the event of interest, for instance, the patient relapsed or died or cured, which is marked with a filled circle, and for some patient, the event of interest during the study period doesn't occur, which is marked with an open circle. Yeah? In time to event analysis, you are not interested in the date when the patient were recruited and when the event occurred. You are interested in the time length or in the observation time, how long the patient were under observation or followed up until a certain event occurred. So we synchronize the data, getting this picture. Synchronizing is done by using a starting point, getting a uniform temporal datum, and the starting point for this case is usually the entry of the patients or subjects into the study, or a different point in time or a point of time. Yeah. Sorry, the point in time of the patient. So you choose as a starting point a certain point, which this point you will define in advance, and this point will be your starting point. And from this point, you measure the length where the patient or subject were followed up or were under observation until the event occurred or not. Question?
I'm not quite sure how you can measure how an event does not occur.
I will explain later.
Okay.
This is special to time to event data. That for some patient the event occurred, and for some patient the event doesn't occur, and how you measure it. This depends on how to say, and how you measure it. This depends on. Okay, yes. If you consider a study, then you contact patients every time. Patients go to the practitioner or go to the clinical center, and then they were examined or asked if there was an event or something else. if the event of interest is death, you can look at the registry and see that the person, the patient which were in the study died or not. Yes? And this is a simple case where you can have the information about the event of interest that is occurred or not. But if a patient relapsed or there is another event of interest, then you ask the patient for this event of interest, if it occurred or not, or you can make the examination directly on the patient and see, okay, there is no relapse or the patient is still in remission. You have to contact the patient to get the information concerning the event of interest.
But then you decide when you measure.
Yes, you decide. You plan a study, and in the planning procedure you will fix when the patient will, how long the patient will follow up, when there will be the next examination of the patient, after 1 year, after 2 years, or after 3 years. This is planned during or before the study will start.
But is it also planned when the event occurs?
No, it's not planned. The patient died,
Yeah,
either the
and
patient
then
died
died.
or died not. So you can't say, so now you have to die.
Yeah, exactly. But you can't measure either when they not die.
But you have the information when the last observation were. Yes. But you contact the person, and so the person is still alive. And then you can look at your calendar and say, the patient were still alive at this time point, or at this date.
But they will not.
And afterwards, you do not consider it because there is no follow-up examination of this patient. So the last information you have from this patient is that this patient is still alive or is in remission up to this date. And there is no follow-up observation of this patient. And so you only have this information up to this date. So this is about synchronization. And you are interested in the observation time or the event time. How long the patient was under observation during the study until the patient was last observed or the event of interest occurred. So there is something special to this time data or to this time to event data. Let me look at, or let me explain it by patient 3. Patient 3, or here you have special is that for some patients or subjects, the event of interest, for instance death or relapse, was not always observed, but only a lower bound of the exact event time is known. That is what I mean, that for patient 4 here in this case, the last examination of this patient was at this date, and there was no follow-up of this patient, and you only have a lower bound of the event time of this patient. You know, at this date, this patient was still alive or was in remission, if you consider relapse as an event of interest, and afterwards, the only information you have is that the event of interest for this patient will occur at a later date, but you don't know when. And for some patients, you already have information concerning your event of interest. Here, this patient died at this date, and you know the concrete date when the patient died. And so you can deduce how long the patient was under observation until the event of interest occurred. And for this patient, you only have the information how long the patient was under observation or was followed up during the study, without an event in this case. Yes, this is special to time to event data, that you have sensor data, that you have patients or information of the data where you know that the event of interest occurred, and you have subjects or individuals or data where you know that the event didn't occur or doesn't occur, but you know a lower bound concerning the event time. This is the last time where the patient were under examination or were observed without an event. So we have the problem of censoring data, and here are some examples where censoring can occur. One example or one reason when censoring occurs is that the subject does not experience the event of interest before the study ends. This is the example of patient 3. No? Patient 3 went into the study at the beginning of the study and then was followed up the whole time of the study. And at the end of the study, after 3 years or 36 months, the patient was still alive or in remission if you consider relapse as an event of interest. And maybe shortly after the end of the study, the patient relapsed. But this patient must be excluded because the study time was from was planned from the beginning of the year 2004 and the end of the study was at the end of 2006. And what happens after this time we are not interested in because you planned the study only for this time period. And so for patient 3 you have the censored datum or you have a censored observation because patient was observed the whole study time without such that the event of interest doesn't occur for this patient. So you have the censored data for this patient. This is one reason where censoring can occur, that the study ends before the event of interest occurs. The second reason is that the subject is lost to follow up during study time. That means that, for instance, that patient 4 moved to another residence or into another region, so that this patient can't be examined during the study because he was not reachable by phone or by mail or something like that. For instance, patient 4 went into the middle of 2004 into the study, and then at the end of 2005, this patient moved to another region, maybe abroad, and so couldn't be reachable for the study. And this is lost to follow up. And so we have the only information that this patient, for instance, was at this date alive or was in remission, because this was the last observation of this patient, and afterwards we can't say anything about this patient. And the third reason for censoring occurs if the subject dropped out from the study for other reasons. How to explain it? If you plan a study where the event of interest is death due to cancer, maybe lung cancer, yes, then the event of interest is dying due to cancer. But maybe a patient 6, for example, here, went into the study at the middle of, year 2004, and then shortly at the end of the study, this patient had a car accident and died due to the car accident. Then we have a concurrent event of interest. If the event in this case, for this example, is death due to cancer, and the patient died due to a car accident, then this is a concurrent event, and so we have to consider this event of this data as a censored data.
What do you call the event? What did you call the event?
For this example, if the event is cancer due to death due to lung cancer or a certain other cancer, and the patient died due to a car accident, then this is a concurrent or an event which is different from the event of interest.
Oh, okay.
The patient died, but not due to cancer, but due to a car accident or an aircraft accident.
What did you call data? And what did you call data?
Data in this case is information which I observed is the time until the patient was under consideration.
I just used a special word after that.
Censored data.
Oh, okay.
This is more. We have in this case censored data or censored information. You measure time and you measure if the event of interest occurred or not, and this is called data, time to event data. And then you have the case if some event of interest doesn't occur, then you have a censored data. for patients where you have the observation time or follow-up time, but we have only the information that this patient or subject was under observation without without any event of interest. Okay, there are 3 reasons when censoring can occur, and due to censoring, we need special technique to handle time-to-event data. The first one, or simplest one, to handle time-to-event data is to omit all patients or subjects having censored data. So, but doing that, you would get invalid statistical inferences and wrong interpretation of the time-to-event experiences. So we need special technique to handle time-to-event data if we have the problem of censoring, or if you consider the problem of censoring. And so in today's lecture, we will learn how to treat time-to-event data statistically, or how to which method can be applied to handle or to examine time-to-event data statistically and interpret the results. And for doing this, I would like to introduce an example where I would explain all the statistical techniques to treat time-to-event data. Here, this is a leukemia study where Freireich, it is an old study from '63, but this is a study with only 42 patients, and so we have a good overview of the methods, and it is a good example to introduce all the methods, because here in this example we can do all calculation by hand. So, this is a clinical trial with 42 leukemia patients, in which the new treatment, in this case, it was a chemotherapeutic substance. To be precise, it was 6-mercaptopurine. I don't know what it is exactly. It is a chemotherapeutic substance. Was compared this treatment to placebo in the maintenance of remissions. The event time studied was from randomization, that is from including into the study, until relapse. At the end of the study, 30 patients had a relapse. This was the event of interest. What is the event of interest? And this is coded for data purposes with 1. And 12 patients with the new treatment remained in remission. For data purposes, this information is coded with 0. So censoring in the data process is censored with coded with 0, and where the event of interest occurred is coded with 1 in this case. This is usual if you analyze time-to-event data. What do we get from this information? That all patients in the placebo group had a relapse, because 12 patients of the treatment groups remained in remission. Here we have censored data of the patients in the treatment group. The purpose of the study was to explore the effect of the treatment, which is coded with 0 for placebo and 1 for the treatment with the chemotherapeutic substance. And white blood cell counts were measured. For data purpose, the logarithm of white blood count cells were examined, and furthermore, the gender of the patient were registered, where female was coded with 0 and male was coded with 1, and the remission time were measured in weeks, which is your event time in this case. The data structure for this example looks like this way. Each row represents the patient, and each column, or in each column, you measure the exposure variable. This is a usual data layout if you perform a statistical analysis with data. You have a treatment column where 1 is the code for the chemotherapeutic substance and 0 for placebo. Here is the logarithm for the white blood count cells, and here is the information concerning gender. And what is new to time-to-event data, that you have 2 extra variables. which constitutes the event time, or time to event data. The first column concerning the event time itself, how long was the patient under observation or contact, and the second or third column measures or gives you the information concerning the occurrence of the event of interest. In this case, if the patient stayed in remission or remained in remission, or the patient relapsed. The event of interest in this example was patient relapsed, which is coded with 1. If the patient remained in remission, then the status was assigned with a 0. So this is special to time to event data. You have 2 extra variables. Here you have exposure variables, treatment, logarithm of white blood count cells, and gender. And concerning time to event data, you have 2 extra variables. One variable which measures the event time, and the other variables which measures the occurrence of the event of interest. So you measure 2 information, as I already said at the beginning. The event time and if the event occurred or not. So due to censoring, we need, as I already said, special techniques to handle such kind of data. At first, we have to estimate the probability of an individual being event-free for a given time period. This can be done by applying the Kaplan-Meier estimator or live tables. And the second part will be that we want to compare time to event data in several different groups. For instance, we want to compare the event time experience in the treatment group compared to the placebo group, which can be done by the placebo group, which can be done by applying the log rank test. And then, last but not least, we want to assess the relationship of exposure variables on time to event data, which can be done by applying the Cox regression. And we want to consider if, as the treatment or the logarithm of white blood count cells or the gender, do they have an effect or impact on the event time, which can be treated or handled statistically with so-called Cox regression. So let me start with estimating of, or with introducing the concept of survival function and the estimation of the survival function, which can be done by Kaplan-Meier estimator or live tables. So there's some a little bit mathematical definition. The user summary for the distribution, or if you consider a random variable in statistics, a random variable in statistics can be described by a distribution. Yesterday we learned about the Poisson distribution. In logistic regression we learned about the binomial distribution. So each random variable or each observation which is random can be described statistically or mathematically by a distribution function, or by distribution of the random variable. Here, for time to event data, we have a special distribution that's called survival function. The survival function is the probability that the event of interest, or that is not the event of interest, or that the event of interest occurs after a given time point t, or that the event time, which is designed with, or which is signed with t, is greater than a given time period t. So you measure the probability, or you want to model the probability that the event occurred after a given time point t. Or in other words, you can, the survival function is the probability being event-free up to time t. So you can say that the survival probability for each time point in your study period, here you have the study period, study time, and for each time point in your study time, you are asked for the probability being event-free, maybe this is your time, being event-free up to that time, or equivalently, you ask for the probability that the event of interest occurred after that time point, maybe here, or here, or here. These are equivalent definitions. So this equal probability being event-free up to time t, or equivalently is the probability that the event of interest occur after the time. Yeah. Here you see a curve of the survival function. The survival function is a decreasing function, starting at 0 with a probability of 1, because at the beginning of the study, all patients are event-free. So the probability that the patient is event-free up to the beginning, or at the beginning of the study is 1. Yes? And the course of the survival function, I already said, is a decreasing function. That means the greater the time course, the more unlikely it is that the patient is event-free. Yes? If you are late, then the probability that the patient or subject will be event-free is getting smaller. Yeah? Because after some certain time, the event of interest will occur for some patients, or for all patients. If the event of interest may be dead, then it is sure that at a certain time point, the patient will die. Yes? Yeah?
Does that mean that you have to find a fixed time point?
No.
You have to-
The definition is for each time point in your study.
Okay, so it's
So you
continuous.
look at each time point, and for each time point, you ask for the probability that being event-free up to that time point. You can ask for the probability being event-free up to this point. You can ask for the probability being event-free up to this point. So you you can take each value within the study time to ask for the probability of being event-free at the time. So you have a continuous course of the survival function. This is the probability for each time here on the time axis. You can calculate, or you ask for the probability being event-free. So you get such a continuous or smooth curve, the survival function. So in theory, the survival function is a smooth function, but in practice, you observe events on a discrete time scale. For instance, days, weeks, or years. Yeah? So it could be expected that this is an ideal form of the survival function, but if you consider data, then you wouldn't get such an ideal form of the survival function. But how the survival function looks like, we will see later if we consider data in this case. So the question is, or the problem is, how to estimate this probability or the survival function for each time point. There are two cases. The first case is an easy case if we have no central data. Then, when the survival function can be estimated using the average number of subjects experiencing the event of interest during the time t or after a certain time t. That is, you count the number of subjects having an event of interest after a given time point t and divide it by the total number of subjects. With the convention that the estimated survival probability at time point 0 equals 1. Let me explain it by the example for the leukemia study, where the placebo group, or where all patients in the placebo group relapsed. Here you can see the time to relapse, which is my event time, and the filled circles represent patients which relapsed. So at after 1 week of observation, 2 patients in the placebo group relapsed. After 2 weeks of observation, next 2 patients in placebo group relapsed. So yes, now we can calculate for each time point the survival probability by this expression. So let me estimate the survival probability at time point 5, or the probability being event-free up to 5 weeks. So we are here. So I ask for the probability that the event of interest or that the patient relapsed after 5 weeks, which is equivalently to ask for the probability being event-free up to those 5 weeks. What I have to do, I have to look at the time point and have to count the number of subjects having event of interest after 5 weeks. So 4, 6, 8, 12, 14. 4, 6, 8, 10, 12. Subjects relapsed after 5 weeks. And the total number of subjects in the placebo group is 21. So the survival probability at 5 weeks is in this case about 57%. If we consider the survival probability at 6 weeks, that is, you ask for the probability being event-free up to 6 weeks, or you ask for the probability that the event of interest or that the patient in the placebo group relapsed after 6 weeks. So you have to count again a number of subjects or patients having event of interest or relapsed. In this case, there are again 12 patients relapsed after 6 weeks. And in total, we have 21 patients under observation. So the survival probability for 6 weeks or at 6 weeks is the same as the survival probability at 5 weeks, because at 6 weeks there are no event occurred, or there's no patient which relapsed. And it is the same for week 7. Yeah. And next, the survival probability at 8 weeks. So you want to ask for the probability being event-free up to 8 weeks, or that the event of interest or a patient in the placebo group relapse after 8 weeks is you have to relate the number of patients having event or relapse. Here in this case, there are 8 patients after 8 weeks who relapse, divided by the total number of subjects under observation, 21, and we have a survival probability of about 38%. So the rest can be done by hand. It's an easy way to calculate the survival, or to estimate the survival probability or the survival function for data if we have no sensor data. What we have to do if we have sensor data? There we need a special method to estimate the survival function or the survival probability, which can be done by the so-called Kaplan-Meier estimator. The Kaplan-Meier estimator is a non-parametric estimation method, and that means that there is no distribution assumption concerning the data. That means you do not assume that the event time have to be normally distributed, and so on. So there is no distribution assumption concerning the time data. And here I want to introduce you to the method how to get a Kaplan-Meier estimator for the survival function. So I think I can make a break now. As the number of slides. So I would like to make a break because what do I need? First I need the event time. The time where the event occurred, which is stated mathematically or in symbols with 0, which is equal to 0 as t0. t1 is the time where event occurred. t2 is the next time where events occur. t3 maybe is the third time where events may occur, and so on and so on. So maybe we have in this case, or in this example, k time points where event of interest occur. In the leukemia examples where patient relapsed. Yeah. At each event time, you count the number of subjects at risk just before time tj. So at t0, you count the number of patients who are under risk having an event of interest. In the leukemia study, you count the number of patients just before time t0. So here at the beginning of the study, of patients who are at risk for having an event of interest. At the event time t1, you count the number of patients and one just before time 1, or before this event time t1, who are under risk for having an event of interest or to relapse in the leukemia. At time point t2, you count the number n2 of patients just before time t2 who are under risk to relapse or having an event of interest. Yeah? This is the number or symbol n2. Or loosely speaking, nj is the number of subjects still in study just before or at time tj. These include patients which are censored or patients having an event of interest. And then you define the number of subjects experiences the event of interest at time tj, which is denoted with dj. So at each time point, you count the number of events at this concrete time point. So t0, t1, so at time t1, there are d1 patients who relapse, or when the event of interest occurs. At time point t2, there are d2 patients relapse, or d2 patients where the event of interest occurs, and so on. So these are the ingredients for the Kaplan-Meier estimator. And from the number of subjects under risk just before time tj and the number of subjects experiencing the event of interest tj, you can count or calculate the number of subjects being event-free at time tj, which is nothing else the difference of nj and dj. So the difference of n1 and d1 is the number of subjects being event-free up to this time point. The number or the difference from n2 and d2 is the number of subjects being event-free up to t2 or maintained in remission. So, in the first step, for calculating the Kaplan-Meier estimator, you have to calculate a so-called conditional survival probability. Let me explain it. Next. So we are at tj and tj plus 1. So we look at the conditional probability that the event of interest occur during this time interval. Here. So at this time point we have nj patients under risk for experiences the event of interest just before tj, and at this time point we have tj subjects experience the event of interest or relapse at this time point. And at time point tj plus 1, there are nj plus 1 patients and day J, D J is one patient experiencing the event of interest. Now we are interested in the probability that the event of interest occur during this time interval, conditional that the patient is event-free up to this time point, T chain. This is the so-called conditional survival probability. So we are interested only in probability being event-free within this time interval, conditioned on being event-free up to the beginning of this time interval. This is the so-called conditional survival probability, and this can be calculated by Nj minus Dj. At the beginning of this time point, we have Nj minus Dj subjects which are under risk for occurrences or to experience an event of interest, divided by the total number of subjects under risk at the beginning of this time interval. Because you forget what is here, and you're only interested in this interval concerning survival probability being event-free during this interval. And this can be calculated by this expression. You calculate the number of subjects which are event-free during this time interval, which is the difference of Nj and Dj, divided by the total number of subjects under risk at the beginning of this time interval. And this is the so-called conditional survival probability. And this can be done for each interval. So you can calculate the conditional survival probability for this time interval. You can calculate the survival probability, the conditional survival probability for this time interval, for this time interval, for this time interval, and so on. And if you calculate each conditional survival probability for each time interval, and by applying the so-called product formula, you get the Kaplan-Meier estimator for the survival probability. So you have to multiply each of these expressions here up to a certain interval you are interested in to get a Kaplan-Meier estimator or an estimation of the survival probability. So if you want to have this estimation of the survival probability being event-free within this time interval or up to the beginning of this time interval, you have to multiply all conditional survival probability up to this time interval to get the estimation of the survival probability. This is the so-called product formula or Kaplan-Meier estimator. So let me explain this this approach via the example of the leukemia patient. Here again, here we have the treatment group, and here again we have the time to relapse. And what is special to the treatment group compared to the placebo group, there are sensor data, which are signed with an open circle, and patients who relapsed are signed with a filled circle. So we need the information about the observation time when the event of interest occurred, how many patients were at risk at the beginning of the event time, how many events occurred at the event time, how many patients are under risk at the event time, the conditional probability, and from this expression we can deduce from the product formula the Kaplan-Meier estimator. I would like to explain the approach for the first three event times. The first event time isn't an event time. This is the time 0. At time point 0, there are 21 patients under risk to experience the event of interest or to relapse. At time point 0, there is no patient who relapsed, and there are at all 21 patients who are still under risk to relapse after time point 0. So the condition or the probability being event-free exactly at time point 0 is equal 1. So the survival probability at time point 0 is 1. So we can calculate the survival probability being event-free up to first week, which is the same as the survival probability for time point 0, because there is no event or no event occurred here at this time point, at this time. When it is interesting to consider this time point, 6 weeks, because this is a time where event occur. So what do I need? Just before 6 weeks, there are events, yes, at 6 weeks, but just before 6 weeks, there are 21 subjects under risk to relapse in this case. At 6 weeks, we have 3 patients with an event of interest, which relapse. And at the beginning, or at this time point, there are 18 patients, 21 minus 3, who are still under risk to experience the event of interest. The conditional probability that being event-free within this time interval, excluding 7 weeks, condition that the patient is event-free up to this week, up to 6 weeks, can be calculated by 18 over 21, which is about 0.857. Applying the product formula, you have to multiply the survival probability for former time points with the survival probability of the actual time point we are considering. In this case, 1 times 0.857 leaves 0.857. So here in this case, or in this count, there are still the censored patient. Because 21 at all minus 3, these are patients who relapsed, and in total there are 18 patients under consideration, including censored data. But what happens at 7 weeks? At 7 weeks, just before 7 weeks, there are 18 patients under risk to experience the event of interest. There are 17 patients. So the censored data is omitted in this case, or is left from the consideration. So we are here, and so this patient, or for this patient here, where censoring occurred, is out of interest. We are calculating the survival probability. So at the beginning of 7 weeks, we have 17 patients which are under risk to experience the event of interest or to relapse. At 7 weeks, there's 1 event occurred, and there are 16 or still 16 patients under risk to experience the event of interest. So the conditional probability that being event-free within this time interval. So we only consider times where event occurred. So this is a time point where an event occurred, and this is a time point. So the conditional probability that an event of interest occurred within this time interval, condition being event-free up to the beginning of this time interval, can be calculated by this expression, 16 over 17. So this is 0.941. So to get an estimate for the survival probability at this time point or later, you have to multiply this probability or this estimate by the 4-point estimate. So you have to multiply 0.857 with 0.941 to get an estimate for the survival probability at time point 7. So the survival probability at time point 7 is here in this case about 80.7%. What about the survival probability at 8 weeks? What would you say?
The same.
It's the same. What would be the survival probability at 9 weeks?
The same.
Yes. And what would be the probability at 10 weeks?
Yes.
Different. But the calculation can be done in the same way. Here we have 2 censored data, and they are left out for the calculation of the survival probability at 10 weeks. So at the beginning of 10 weeks, there are a total 15 subjects under risk to experience the event of interest. At 10 weeks, there's 1 censored data and 1 observed event. So we have 1 event. In total, we have at the beginning of 10 weeks 14 patients who are under risk to experience the event of interest after 10 weeks. Again, the conditional probability, and here we have the survival probability. by multiplying foregoing numbers with this conditional probability. So this calculation can be done and so on and so on and so on. And so you would get the estimation of the survival probability for the whole study time. Yeah?
Can you please explain again why you need to multiply the numbers with the survival probability?
Because this is the survival probability being event-free within this time interval, condition being event-free up to this time interval. So you are interested in the survival probability being event-free after this time point. So you have to multiply the conditional probability to get the right number for the survival probability being event-free at this time point.
Is it important that the numbers
So maybe you are interested here in survival probability being event-free up to this time. What you do by calculating conditional probability or survival probability is you calculate the probability being event-free within this time interval, condition being event-free up to this time interval. So the conditional probability is only this, I would simply say yellow line, but you are interested in the probability being event-free up to this time. So you have to multiply the foregoing conditional probability to get the probability being event-free up to this time. Yeah? It's okay? It's the same if you are here in this interval. Here you calculate the conditional probability for being event-free within this time interval. Condition being event-free up to this. So to get the estimation for the probability to get an estimation for the probability at this time interval, at this time point, maybe p tilde, you have to multiply this conditional probability with this conditional probability. That's why you get the product formula. So the conditional or this conditional survival probability, which is calculated in the first point, only considers this interval and forget what happens before this interval. Or here again, the conditional survival probability only restrict or considers this interval and forget what happens before. But you need the information what happens before or which survival probability occurred before, and then you multiply these conditional. So getting the Kaplan-Meier estimator by data, you have to perform 2 steps. The first step you have to do always if you perform survival analysis in data. At first you have to define the so-called survival data set. Or survival, event time data set. ST stands for survival time and Z for Z. Yes? At first you have to define event time data or survival time data, which is done by the standard command stz, followed by the time variable, and followed by the event variable, where the event here is defined as failure. Event and failure is quite similar in Statics data. So failure defines the event, or with the notation of failure you define the event, and the event, if you think of the data layout, was designed with or designated with status. And the event of interest was relapse, and this was coded with 1. So the event here, which is in brackets after the command failure or the failure option or event option, is status equals 1. So with this expression, you say data that the event is coded with 1, and all other events or other codes of the status variable, for instance 0 or 2, is considered as a censored data. It's data. Yeah? So here you say data that the event of interest, in this case relapse, is coded in your data set with 1, And all other codes for this variable status, for this status variable, which is 0 or maybe 2 or different from 1, is handled as sensor data instead. Yeah? So this is the step you have to perform if you apply or if you want to perform time to event analysis in this data. So to get the Kaplan-Meier estimator, after that you have defined time to event data you can get from the STS command if you apply list. And here if means that we only want to get the Kaplan-Meier estimator for the treatment group. Treatment group was coded as 0 and 1. 1 was the group getting the chemotherapeutic substance, and 0 was the placebo group, or the code for the placebo group. So this is only a restriction of the data, and here I want to restrict only on to the treatment group. And then you get this table where the survival probability concerning especially Kaplan-Meier estimation is presented. At the first column you have all observation time, including censored time and event times. Yeah. On the in the second column there are the number of subjects under risk at the beginning of each time, which is in our case NJ. In the third column there are the number of events or of patients who relapse, which here in this case is denoted with D. But here you have times where also sensor data occur, so you also measure sensor data or count sensor data, which can be done or which is written in the fourth column denoted with net loss. In this column the number of sensor data is designated or summarized. Using the same formula, product formula and conditional formula for the conditional probability, you get here the survival, the estimation for the survival function, which is called instead of survival function. It's the same as survival function. Including the standard error of each probability or of each estimate and 95% confidence interval. If you compare these results only where event occurred, these are deep time points, then you see that the calculations made by hand leaves the same values compared to the values given in this class. If you look at this time or this time, you will see that it's the same value. For this simple case of 42 patients, calculation can be done by hand. And for other cases, if you have a data set of 1,000 or 2,000 patients, then you perform it by hand. So you can invoke data to give you a table of the survival probability. So these are all the numbers.
The command
STS, survival time, I have to look. Survival time statistics. STS, survival time statistics, please, and list is the command to list the survival probability as a table. And if means that I want to restrict only to the treatment group. So if you omit if and this expression, then you would get a survival table for all 42 patients, including patients having or including patients from the placebo group. So these are only numbers, so this is fine. But to represent the Kaplan-Meier estimator, the best way to do this is to plot the so-called Kaplan-Meier plot. So in the Kaplan-Meier plot, the Kaplan-Meier estimator are plotted. These numbers here, which are in this column, are plotted against what the probability in the foregoing table is plotted against the time variable. Yeah? So you get a step function, the appropriate command for getting the Kaplan-Meier curve or the Kaplan-Meier plot is survival time statistics followed by a graph. And here I want to have separated graphs, one for the treatment group and one for the placebo group. That's why this by statement. And here this option signs that you want to have the information concerning sensor data. The sensor data are signed with a small line, vertical line. Here at this time there are sensor observations. So what you see is the curves of the survival probability. At the beginning I said that the survival probability has this curve or course, the smooth course, and because due to that you handle with data, with discrete data, you get a step function for the Kaplan-Meier estimator. For the estimation of this smooth curve, you get from the Kaplan-Meier estimator this step function. Yes. This is a function or the survival probability or estimation of this smooth curve based on data. Finally, this is step function. Step size is dependent of the number of subjects under risk at this time and how many events occur at this time.
So this is the final output we
Yeah.
need to interpret. Okay.
Because I'm not sure if you want to deal with this. So here with the Kaplan-Meier plot you get an overall impression of the event time experience in this case. And this is more informative as this table with the survival probability, this plot. So from the plot you can say deduce the maximum observation time in each group. In the placebo group, the maximum observation time was about 35 weeks. And in the treatment group and in the placebo group, this was about 23 weeks. We only need to look at the end of the survival curve to see or to deduce what is the maximum observation time in each group. So, what we can see again, we can see that for the placebo group, the survival, the Kaplan-Meier plot drops to 0. Why? Every patient in the placebo group relapsed or experienced the event of interest. If in one group or if you have data where the event of interest occurred for every individual or for every subject, then the Kaplan-Meier plot drops to 0. For the treatment group, you see that the Kaplan-Meier curve is above 0. That means the last event occurred at about 24 or 23 weeks, and all events afterwards are censored events or censored data. And so the Kaplan-Meier curve for the treatment groups keeps or stays at this level, because no event occurred after the last event occurred.
And how can you see how many events occurred?
You can't see it.
You can't see that.
You can't see it.
Oh, you can only see that.
For this you have to
Okay.
take this table to see how many events occurred at certain time points. But from the Kaplan-Meier estimator, you can't see it.
So the
because
length of the steps
it's
doesn't mean.
no. The length of the steps is dependent on the number of risks of patients, which are depends on the number of risks of patients at this time point and how many events occurred.
Okay.
And you need information how many numbers at this point, time point, at this, and how many events occurred. To get information how long this step size is.
Okay.
So it's better to take this table if you are interested in the concrete number of events at a certain time point, and here they only had an overall impression concerning the survival probability, the course of the survival probability. You don't get the information, there are 2 events, or there are 2 events, or maybe here there may be also 2 events occurred. You can't deduce it from the step size.
Can you say again, after 23 weeks treatment group, the rest of the patients, they could what? They were censored?
The last event was at 23 group, 23 weeks in the treatment group, and afterwards no event occurred, but only censored data.
Okay.
But in the calculation of the Kaplan-Meier estimator, censored data are left out from the calculation. And so there is no step downwards in this case, because there is no event occurred on no event occurred after the last event occurred.
So what is the final conclusion?
The final conclusion is,
Yes.
what could you deduce?
But I'm just I'm losing track of what we wanted
Yes.
to find out.
Finally, you want to compare the survival of the time to event experiences between placebo and treatment
Yeah.
groups. No. If I consider these estimates or my estimates, what can I use? I would say that the event time experience in the treatment group
Yeah.
is better compared to the event time experience in the treatment group, placebo group.
Okay.
Due to less probability or survival probability in the placebo group compared to the survival probability in the treatment group. And you can say that this difference is overall, or the whole duration or observation time of the study. At each time point, you can see without the first 2 weeks, I think, but at each time point, you can see that the event time experience in the treatment group is better in the sense of survival probability compared to the placebo group at each time. But there are also examples, I think in the exercise there will be an example where the survival curves or the Kaplan-Meier plots crosses each other. These are, this is the survival curves, for instance, or the Kaplan-Meier plot for the, maybe for the treatment group, and this is the Kaplan-Meier for the placebo group. So what you can deduce here from this picture is that the time to event experience in the treatment group is better compared to the placebo group up to this time. And after this time, you have a different picture. That means that the survival or the time to event experience in the placebo group is better compared to the treatment group. Yes. This is what you can deduce from the Kaplan-Meier plot. Okay. So this is an overall impression of the survival probability. From the Kaplan-Meier plot, you can deduce several measures to interpret or to compare treatment groups with the placebo group. These are the median event time or special survival probabilities, which I will explain next. So from the Kaplan-Meier plot or estimation, you can estimate certain survival probabilities. For instance, you want to estimate the proportion or the probability being event-free at 10 weeks. This can be deduced from the Kaplan-Meier plot by plotting a vertical line at 10 weeks. And at this point where this vertical line crosses the Kaplan-Meier plot, you can read off the value at the probability axis or the y-axis to get an estimate for the probability being event-free at 10 weeks. So in the placebo group, you would estimate an survival probability, or you would estimate at 10 weeks survival probability of about 30%, 40%, and in the treatment group you would estimate survival 10-week survival probability of about 75%.
But you can also see that on the list, right?
Yes.
Yeah.
You can see it also on the list.
But only for the treatment group.
No, yes, in this case only
Yeah.
for the treatment group. You can see it here from the list.
Yeah.
So you have to look at techniques, and you can deduce the survival probability. In this case, is 75%. If you should I do it? Yes, I can. If you ask for the 15 weeks survival probability, it means for the proportion being event-free up to 15 weeks, or that the event of interest occurred after 15 weeks. Then you can take this list. You have to look where 15 weeks may appear, here in this case, between 16 and 17 weeks, but where I have to read up or read off the appropriate survival probability, I have to, here,
Yeah.
13 and 16 weeks, excuse me, 13 and 16 weeks, and so you have to think which line or which appropriate survival probability I have to read off in this case. And if you have this list of survival probability and you want to estimate a certain survival probability for a given time period, and this time period isn't an event time, then you have to take the value before this time.
Oh, okay.
So
So
you have to
13.
look at 13 weeks. If you are interested in the 15 weeks survival probability, you have to look at the line of 13 weeks, and there you can get a 15-week survival probability of about 69%.
But it is just because on the graph, is it just an estimate, or is there some
It's
sort of
an
command
It's an
instead?
estimate for the population.
So you just
You can't say in
It's-
general the 10-week survival probability for the whole population is in the treatment group 25%.
Okay.
It's only an estimate.
Okay.
So estimate has some uncertainty, which is given here in the 95% confidence interval. So you can say the 10-week survival probability in the treatment group is 75% about, with a standard error of about 0.1, and the confidence interval here in this case is from 0.5 to 0.88. So you can expect that each value in this may be the appropriate 10-week survival probability. So this is only an estimate. So estimating survival probability, and also you can estimate a certain event time. In this case, I will introduce you to the median, or let's explain median event time. This is the most interesting time or measure to describe time to event data, which also can be deduced from the Kaplan-Meier estimator. The median event time is a time beyond which 50% of subjects or individuals in the population are expected to be event-free or under risk at this time point. So you look at the probability, or at this time point, where the probability being event-free up to this time point is exactly 0.5. So that 50% of subjects are under risk to experience the event of interest after this median event time, or equivalently 50% of subjects are event-free up to this median event time. So this is a general definition of the median event time. If you know the survival function, you can deduce from this expression the median event time. But you have discrete data, you have to estimate the median event time from your data. For this, here I have the definition or the expression how you can calculate the median event time by hand. You have to consider only time where an event occurs. This is denoted with Tj. And at this time point where the survival probability is less than 0.5, this time point, the smallest time point, constitutes the median event time. So, but this can be deduced very easy from the Kaplan-Meier estimator. From the Kaplan-Meier plot, or in the Kaplan-Meier plot, you have to plot or draw a horizontal line at 50% survival probability, and at the point where this horizontal line crosses the Kaplan-Meier curves here and here, you can read off the appropriate value from the time axis to get the median survival time or event time. So for the placebo group, the median event time is about 8 weeks, and for the placebo group, for the treatment group, the median event time is about 26 weeks. Of course, these numbers, 8 or 23 weeks, can also be chosen from the list of survival probability. That means you can read off, you can get the median survival probability also from this table. What you have to do, you have to look at this is all, first for the this is for the treatment group. You have to look or you have to search where maybe would be the value of 0.5, 50%. This value would be like between these two survival probabilities, and there are there are events after 22 weeks and after 23 weeks. So in this case, if the survival the 50% the median or 50% is between two survival estimates, then you have to take the lower one to get the estimation of the median event. For survival probability, you have to take the upper one to get the appropriate survival probability. For the median survival, for the median event time, you have to take the lower line or row of this table to get the median event time. So you have to look at this column where the value of 0.5 may be light. This would be like between these two survival probabilities, and you have to take the line with the lowest survival probability and diffuse the appropriate median event time. In this case, 23. Sometimes it is hard to deduce the survival probability from the Kaplan-Meier plot in the way which we have done here, or the median event time from the Kaplan-Meier plot in the way which we have done here. Sometimes it's not unique to get concrete survival probability for a certain time or the median survival probability. This is, for instance, if you have such a survival curve, then it's hard to find a concrete or a good estimate of the median survival probability or certain of the median event time or a certain survival probability. So for in this case, it would be better to deduce these measures from the list. So, next thing, how to estimate survival probability is using life tables. Here I do not want to go into details due to time. Life tables is a summary for large complex data set. And the difference between Kaplan-Meier estimator and life table essentially is that Kaplan-Meier estimates the survival probability at each time point, and life tables estimates the survival probability within a certain or given time interval. Yeah. So the idea is that you have TJ or the TJ is the defines individual event or censoring time. So you include for calculating life tables also the censoring times for consideration. And what you are doing for life tables is that you separate the time axis in several intervals of equal length, such that in each interval there are enough events. So for this example of the leukemia study, there are 8 intervals of length 4 months. And in each interval there are several events occurred, or there are several patients who relapse. This is the idea, and the differences between the Kaplan-Meier estimator is that for live tables we estimate survival probability for this interval and not for a concrete time. Yeah? And this is the difference. But I do not want to go into detail for estimating or how to get the estimation for live tables. This is quite similar to Kaplan-Meier, but the difference is in live tables you estimate the survival probability within a time interval, and in Kaplan-Meier, or for the Kaplan-Meier estimator, you estimate the survival probability for each concrete time point. So if you want to invoke live tables with data, the appropriate command is ltable. Have a mind, or having a mind that you have defined survival time set, ST set in Stata. So Stata knows what is the time variable and what is the event variable. Yes. Think of the STZ command here. If you initialize this one, you only need to initialize this one once. Yes. If you are working with time to event data, you only have to initialize it once. Yes. So Stata knows that you are working with time to event data, and you can perform Kaplan-Meier estimator, and afterwards you can get the live table, or can apply the live table command, which is ltable followed by the time variable, followed by status or event variable, and then you have to say how the length, or which you have to configure the length of the interval you're considering, and what you want to estimate the survival in this case. You can also estimate the probability of dying or failure or something else. But here you are interested in survival, and as I already mentioned, this time axis is separated in several time intervals, in total 8 time intervals of length 4 weeks, and for each time interval the survival probability is estimated similarly to the Kaplan-Meier estimate. Yeah?
Is this because the intervals is 0 to 4 and then 4 to 8, but is 4 included in the first interval and in the second, or how is that?
That's why I omitted the slide. The first time is included, and the second time or the last time not.
Okay.
So in this expression, or in this example, in the first interval 0 is included or not.
4 now.
In the second interval 4 is included and 8 not. In the third interval 8 is included, 12 not. This is only configuration. You can also say, okay, for this interval 0 is included and 4 is included. For the second interval 4 is excluded and 8 is included. It depends on the definition.
But it's pretty important to.
Yes, it's important
Yeah.
to because at time 4, if you would say that 4 is included in the first interval, you have more events compared to this case where 4 is included. So there are differences. But it is only an estimate. So and I think it, due to it's an estimate, it makes no difference if 4 is. No. No, I'm wrong, because you are interested in ensure of quite correct estimation of the survival probability during a time interval. And the definition of survival function is being event-free up to, or that the event of interest occurs after this time. So it should be, or it is plausible that if you consider like table, look calculate 1 to
The right side.
right side is the upper bound of this interval is excluded in the lower bound. It's the same for the definition of the conditions about probability, where the lower bound is included in the calculation and the upper bound not. Because you are interested here for survival probability being event-free up to this time, or that the event occurs after that time point. So, as we have seen from the Kaplan-Meier estimator, placebo patients or patients from the placebo group differs from patients in the treatment group with respect to the event time experience. Yeah. So this is only a description, but there are tests to compare the time to event experiences between different groups. This can be done by the so-called log-rank test. The assumption for the log-rank test is that we have proportional hazards. I will explain later. And the hypothesis or the null hypothesis is that there is no exposure effect. This means there is no therapy effect concerning the event time or time to event. Or alternatively, the null hypothesis is that the survival functions are equal in both groups. It means the survival function in the treatment groups is the same as the survival function in the placebo group at each time point. This can be tested using the log-rank test, and the log-rank test is based on the statistic of chi-squared type to compare the expected with the observed number of events occurring. So, I'm not sure if you are interested in the mathematics of the log-rank test. The log-rank test, short, for each time point where an event occurred, you consider such a table where you count the number of subjects having an event of interest in both groups and how many subjects are under risk. And for each table, you calculate the expected number of events. Here, this is the observed number of events, which you can deduce from your data. Yeah? And the log-rank test compares the observed number of events with the expected number of events if the null hypothesis is true, if there is no differences. So it means if there is no differences between the survival function or the time to event experiences. From this null hypothesis, you can deduce or can calculate from this type, from this table for each event time, so-called expected number of deaths. And the log-rank test compares the observed number of deaths with the expected number of deaths, which is calculated under the null hypothesis. Doing this calculation leaves this table. Can also be done by hand, but here I do not want to go into detail. Here we have these two groups, treatment group and placebo group, and here we only consider in both groups the event times, or times where event occurred. And they are listed here. And then we count the number of events in each group at each event time, in this case. So for the placebo group, the first event time is after 1 week, where in the placebo group there are 2 events, and in the treatment groups there's no event. So 0 and 2, and all we have 2 events. And then in total we have 21 patients under risk in the placebo group at 1 week, and 21 patients under risk in the treatment group at 1 week. In total we have 42 patients under risk. This number divided by this number is the expected number of patients, or is the probability having an event of interest or to relapse at this week. So we would expect that about 1/21 patients of these 42 patients would relapse at 1 week. Multiplied by the number of patients in the treatment group, 21, yields the number of expected deaths or patients having an event of interest. In this case, the expected number is 2. Specific case. So the probability, or you expect that at time at 1 week there would be 1/21 events. So the probability that an event occur at 1 week would be 2/42 or 1/21, multiplied by the number of patients in the treatment groups yields the expected number of events in the treatment group. In this case, the expected number of events in the treatment group is 1. Let me explain for the 4th line. No, 6th weeks. At 5 weeks, there are no events in the placebo group, no events in the treatment group, 2 events in the placebo group. In total, we have 2 events. And in the placebo group, in the treatment group, there are still 21 patients under risk to experience the event of interest. And in the placebo groups, there are still 40 patients under risk at this time of 5 weeks. In total, we have 35 patients under risk to experience the event of interest, in this case to relapse. The number of events at this time point divided by the total number of subjects under risk is the probability having an event after being event-free up to this time point. Multiplied by the number of patients in the treatment group, in this case 21, yields the expected number of events in the treatment group at 5 weeks. The expected number compared to the observed number yields the difference between observed and expected. And we have some uncertainty in our data, which is expressed by the variance of the expected or of the observed number of deaths or events. Zooming up the rows yields the total differences between observed number of events compared to expected number of events. And here you have the total variation in your data. And these two quantities yields the so-called log rank test, or as the basis for calculating the log rank statistics. The log rank statistics compares observed number with expected number divided by the variation in your data, usually speaking. And this test statistics is chi-square distributed with 1 degree of freedom under the null hypothesis that the event time experiences doesn't differ between both groups. If you invoke the log rank test in Stata, the appropriate command is STS, survival time statistics, followed by the test. And what would you compare is designed by the exposure variable treatment. So you want to compare placebo with treatment group, and there are several tests for comparing survival function. Here, if you apply the log rank test, you would get the log rank test. There are other tests, for instance, the Breslow test, or the Tamarone test, or Terone test, or Petro test to compare survival function. But the log rank test is the easiest one to apply. There are differences between the other tests, but I don't know to explain it why. It depends on censoring. How many sensor data you have at the beginning of the study or at the end of the study, and from this depends the choice of the appropriate test, Breslow test or Terone test or Pedo. The log rank test is the simplest one. So, okay. To invoke Stata to get the log-rank test, use this command, and then you would get this output, where you have your both groups, how many events were observed, and the number of expected events, which you can get from calculation by doing by hand, using this approach. And zooming up, you would get the number of events. If you're zooming up events observed, you have 30 events in total in your data. And this number must, or the expected number of events equals the number of observed events. So the test statistics relates observed events with expected events, which gives a number of 16.79. If you take the calculation by hand, you get the difference of 10.225, and for the variance you get a value of 6.257. And if you take this formula, you would get the same value of the test statistics of 16.79. So here the results are the same if you do the calculation by hand or if you take data to perform your calculation. So this test statistics explains that there is a great discrepancy between observed and expected events, and so you can be sure that there is a difference between the survival or event time experience. And this can be deduced from the p-value. The p-value is in this case less than 5%, and so you would deduce or you would reject your null hypothesis that the time to event experiences in both groups are equal, and so you would deduce that there are differences in the survival probability or survival function for event time experience. So that means that both groups, placebo and treatment groups, differ with respect to the event time. That means you have to prove, or you have to, via applying a statistical test, prove that there is a difference between the survival experience or event time experiences between treatment group and placebo group.
But the number 16 points, what does it say?
16 points. 16?
16. The number,
This
what
is-
does it?
This is the value of the test statistic, which can be calculated in such a way. This means it's only a measure how far are the observed number of tests compared to the expected number of tests.
But is it a
Is-
great number or
It's a
small
great number. If the number is 0, then the observed number equals the expected number, and then you would accept the null hypothesis. And the amount, how far away the test statistic must be from 0 is deduced from the chi-square distribution. This is the basis which says this is a great value or not. And this information is summarized in the p-value. You can't work with this number. It's only a value of the test statistics to inform you how far you are from the null hypothesis. But you can't deduce from this value I'm far or not, because this depends from the sample size, how big or how many data you have. It depends how many events were observed in your data. And you can get the test statistics with the same value, but with a p-value greater than 5%. So the information concerning the sample size and how many observed events and the value of the test statistics is summarized here in this p-value. The p-value gives you some information about the evidence concerning the null hypothesis. The smaller the p-value, the more no evidence you have concerning the null hypothesis. And it's the same way here. The higher the q-value or the value of the statistics, the more no evidence you have concerning the null hypothesis. But you can't say this is much or less. That's why you look at the p-value.
But if the number is closer to 0,
then you would expect
8, 0.
if the number may be, if the number is for instance 5 or 6 or 7, then you might say, or you might deduce that there is no discrepancies. That the NAR processes can be accepted, but you're not sure because it depends on the sample size and how many events you have.
But that would also show in the p-value.
Yeah, this summarizes it.
Yeah.
Yeah, was a question? Okay. So,
Could we take a break?
yes, of course. Oh, question of the hazard. The hazard is, can you understand as an instantaneous incident rate. The hazard is a function with respect to the type. So you have a function which depends on the time and is the probability of an event in an infinitesimal small time interval, given that no event occurs up to time. What does it mean?
Okay, du bist gerade.
Here we have our time axis, and we are interested in the survival probability within the time interval t up to t plus delta. So if you look at the survival probability or the being event free within this time interval, condition that this line means condition that you are event free up this time. So you ask for the probability of experiencing an event of interest within this time interval. That means that an event occurs in this time interval, condition that no event occurs up to this or up to the beginning of this time interval. And what you are doing is that you decrease the length of the delta of the interval. That means you're letting delta getting smaller, smaller, smaller. That means you take the left border of this interval and switch it to the left border of this interval to get the hazard rate. The hazard rate is also called the short-term event rate for subjects who have not yet experienced the event of interest at time t. Okay, loosely speaking, the hazard rate is a rate, or gives you the information about how, or how to say, I think, this is. The hazard rate is a certain probability. It's not exactly a probability, but it's a measure that gives you about the information about the rate that you are event-free up to time t, and just at that time you will experience the event of interest. The hazard rate you can loosely speaking as a rate that you are event-free up to time t, and just at that time you will experience the event of interest. So, in other words, the hazard rate is the rate that you survive up to time t, and just at that time point t you will die. And this number gives you the hazard rate.
So the hazard is also can also be dying.
Yes. It depends on the event of the event
Yeah.
you consider.
Okay.
For the leukemia example, the hazard rate is the rate that you are remain in remission up to time t, and just in time t you relapse. So the hazard rate for that, for instance, is you are survive up to time t, and just at time t you die. So if you consider the event dying due to cancer, then the hazard rate is the rate for time t that you are still alive at time t, and just at time t you die due to cancer. Yes, the hazard rate depends on the event that you are interested in. Yeah?
So you just find a more precise event time for the event.
Mhm.
Okay.
Is it used as a
No, it's a summary for time to event data, like the survival probability.
Alright.
So you want to describe survival time to event data. The first one you describe them by estimating the survival probability. And another measure or quantity to describe time to event data is the so-called hazard rate. Yes? And there is some equivalence between survival probability and hazard rate. Forget the mathematics. The only information what you should take from this slide is if you know any one of the functions, if you know the survival probability function, you can deduce the hazard rate function, vice versa. If you know the hazard rate function, you can deduce or you can get the survival probability function. So there is an equivalence between these two quantities, survival probability or survival function and hazard rate. Here's a small example for constant hazard rate. Here I assume that at the whole time course we have a constant hazard rate. It means the rate that an event of interest occurs is the same at each time point. Yeah?
Can we also say that hazard rate measures the probability of having the event of interest 8 times t?
No.
It's not the
It's a
same.
rate. It's a rate because you divide by the time. The definition of hazard rate here, formula for the hazard rate is that you have in the denominator a probability, and this probability is divided by the time length. And so the hazard rate isn't a probability because the hazard rate can take numbers which can be greater as 1. Here you will have an example. Here is the hazard. Here you have an example for a hazard rate which is 0. The hazard rate can take values greater than 1, and so it can't be a probability because a probability can only take values between 0 and 1. So you can't interpret the hazard rate as probability. No, we can't interpret the hazard rate as a probability. It is a rate which gives you information concerning the speed. Yes? The speed, how schnell, wie schnell?
How fast?
Schnell?
Fast?
How fast?
Yeah, he's from East Germany, Jena.
Gives you
Yes,
information how
Western
fast an
side.
event
You know,
occurs at a
Leipzig.
certain time point.
He's talking
So,
very
this is no information concerning probability. Calculation based on probability, but here you get information how fast the event occurs at a certain time. So here is an example, a simple example of a constant hazard rate. That means that the experience or the occurrence of an event, for example, relapsing or dying, is almost the same at each time point. And here you have the equivalent concerning the survival function, and there is and you can deduce that from this picture that larger hazards are directly related to shorter time to event data with respect to smaller survival probabilities. So you have a large hazard, and that means that the survival probability or survival function for larger hazard is smaller compared to the survival function with respect to a smaller hazard. So that means that a large hazard, means that you have a shorter survival, smaller survival probability, means that you have shorter event times. Applying the log-rank test assumes that assumes the so-called proportional hazard. That means if you consider the hazard for the treatment group and you compare the hazard rate in the placebo group, then the quotient and the relation should be constant over the whole time course. Yeah? This is the so-called proportional hazard assumption. That hazard in the comparison or exposed group, which here in this case is the treatment group, should be almost the same or proportional to the hazards in the reference group or unexposed group, or in this case the placebo group. This is the so-called proportional hazard assumption. This hazard assumption do we need to perform statistical tests like the log-rank test, to estimate the hazard ratio, or to examine the influence of exposures to time to event data, which is summarized in the so-called Cox regression. How can we deduce if the proportional hazard assumption is fulfilled? Forget this slide. You can examine this assumption by using ST-PH plot data. ST for survival time, PH for proportional hazard plot, separated with respect to the treatment. One plot for the placebo group and one plot for the treatment group. The diagram or this proportional hazard plot is based on the estimation via the Kaplan-Meier estimator. So here you see log of the proportion or of the survival probability is plotted against the logarithm of the time. Here in this case time to relapse. And here you have the survival probability or the probability maintained in remission or to relapse after a certain time point. And what you see is, or what is pictured here is the log of the survival probability against the logarithm of the time to get an almost linear curve of these functions. So if these functions are quite parallel or have a parallel curve, then you can deduce that the proportional hazard assumption is fulfilled.
So, what do you say about that one?
What did you say? It's quite parallel,
Yeah.
I think. If you optimize it and you draw a line here and a line here, then you would deduce it's quite parallel. And so the proportional hazard assumption is fulfilled in this case. But if you have another picture, log time, and you have minus log to the dip, and you have such a curve, then you would deduce there is no parallel curve. And if you have such a thing, what would we deduce? It's also parallel. Yeah? And here you would say, okay, the curves have a parallel curve, and so the proportional hazard assumption is fulfilled. But by the logarithm of the time axis, you almost get such a linear trend. So, let me come to the main topic of today's lecture. Cox regression. So the aim of Cox regression is to relate exposure variables or multiple exposure variables which may be qualitative, for instance sex, or gender, or quantitative, which may be age of patients or the BMI of the patient, to a time to event outcome. And this is done by modeling the hazard function. Yes. So as in logistic or Poisson regression, this approach can be used to learn about exposure effects while correcting for other variables. This concerns you can consider interaction and confounding again, or also in Cox regression, like in logistic or Poisson regression. Okay, what we are doing is that we model the hazard function with respect to key or sub-exposure variables, which might be gender, age, BMI, or for the leukemia study where we measure the logarithm of white blood count cells and the gender and the treatment. These are our three variables, and the idea is to model the hazard function as a product of the baseline hazard and e to the power of the linear combination of the exposure variables. So the baseline hazard is the hazard function for the subjects where all exposure variables is 0. You can think of the baseline hazard as the hazard for a reference subject in your population or in your data. So baseline hazard is the hazard for choosing reference subject, or nothing else as the hazard if the exposure variables are all 0. So Cox regression tries to model this hazard function independent of the exposure variables and the time as the product of the baseline hazard and the exponentiation of this linear combination of the exposure variables. So the Cox regression model is single parametric in the sense that the baseline hazard doesn't need to be specified in advance. And the coefficients, which are theta 1 to theta p, are estimated via so-called partial likelihood estimation, comparable to maximum likelihood estimation. So how to interpret the coefficients? The regression coefficients, beta 1 to beta p, these concerns the coefficients for the exposure variable, represent the effect of the exposure variable. Beta g, which is the regression coefficients of the chased exposure variable, is the effect when we have corrected for the other exposure variables. What does it mean? Or how we can interpret this regression coefficient. Can be interpreted as a term in terms of a relative risk. Relative risk here in this case as the so-called hazard rate ratio. That means you calculate the ratio of two hazards. Hazard function of one group divided by the hazard function of a different group constitutes the hazard rate ratio. The ratio of two hazards is the hazard rate ratio, and the coefficient beta g can be interpreted as the hazard rate ratio in such a way that if we increase one exposure variable by 1 and fixing the remaining exposure variable, then you can get the hazard rate ratio as the exponentiation of the appropriate regression coefficient. This is quite technically and mathematically, so let me explain it. What does it mean for the example of the leukemia study? In first case, I consider the Cox regression model for the remission type with two exposure variables, which are the treatment and the logarithm of white blood count cells. So I would like to model the hazard function as a product of the baseline hazard and e to the dependence of treatment and the logarithm of white blood count cells for each time point as the product of the baseline hazard and exponentiation of this linear combination, the exposure variable, treatment, and white blood count cells. If the logarithm of white blood count cells is 0 and the treatment is 0, this constitutes the reference subject. And for this reference subject, you have this baseline hazard. Yeah? So, what does this coefficient beta 2 or beta 1 means? For the exposure variable, which constitutes the treatment, which was coded with 1 as the treatment, this is chemotherapeutic substance, and 0 with placebo, we have the following. At first, we calculate the hazard for the treatment group, keeping the logarithm of white blood count cells constant. and relate this hazard to the hazard function in the placebo group, keeping the logarithm of white blood count cells constant. Taking this expression, what would we get? Baseline hazard time e to the power of beta 1, because treatment in this case is 1, plus beta 2 times the logarithm of white blood count cells, divided by the hazard for the placebo group. So it's equal to the baseline hazard times e to the power of beta 1 times treatment, but treatment in this case is coded with 0, so this expression or this terms drops out, and it remains this expression, beta 2 times the logarithm of white blood count cells. These two expressions and these can be cancelled or cancelled out, and it remains e to the power of beta 1. So you get an expression for the regression coefficient beta 1. That means e to the power of beta 1 is the hazard rate ratio to relapse in the treatment group compared to the placebo group, adjusted for the logarithm of white blood count cells. And you can interpret this term e to the power of beta 1 that the hazard of the treatment group is e to the power of 1, the hazard of the placebo group for fixed logarithm of white blood count cells. It's almost the same as the odds ratio or the incidence rate ratio, where the regression coefficient, if you exponentiate the regression coefficient, you get in logistic regression the odds ratio, or the interpretation for the regression coefficient as the odds ratio, and in Poisson regression you get the interpretation for the regression coefficient as incidence rate ratio. But in Cox regression, where the object is to model time to event data, the regression coefficients beta 1 for the exposure variable have the interpretation in terms of hazard rate ratios. Yeah? Because in Cox regression we model the hazard function. So this is the interpretation for a qualitative variable, that is they consider treatment with two possible values, 0 for the placebo and 1 for treatment. And what about quantitative variable, which is, for instance, the logarithm of white blood count cells? How we can interpret the regression coefficient for the logarithm of white blood count cells? We can do the same calculation. At first, we calculate the hazard function for a certain treatment group, maybe a placebo group or the group which is treated with the chemotherapeutic substance, and add to the logarithm of white blood count cells 1, and divide this hazard by the hazard for a certain treatment with respect to the logarithm of white blood count cells. So we add a 1 to the logarithm of white blood count cells, and substitute or can simplify this expression where we substitute this logarithm of white blood count cells by the term logarithm of white blood count cells plus 1 divided by this hazard. So these two terms drops out or can be cancelled, and this term can be cancelled too, and it remains the expression or the exponentiation of e to the power of beta 2. So increasing the logarithm of white blood count cells by 1 unit means that the hazard rate is e to the power of beta 2 higher compared to the hazard if the logarithm of white blood count cells is not increased by 1. So the interpretation of this regression coefficient is that increasing the logarithm of white blood count cells by 1 unit implies a change of the hazard by a factor of e to the power of beta 2 for treatment fixed. So for each group, for treatment group or for the placebo group, increasing the logarithm of white blood count cells by 1 unit means that the hazard increases or decreases by a factor of e to the power of beta 2. Y decreases or increases. As I already mentioned, the hazard rate ratio is the ratio of two hazards, H1 and H tilde 1. This is the hazard of some combination of exposure variable, and this is the hazard function different from a okay. In the denominator, we have the hazard function for a certain combination of exposure variable, and in the numerator, we again have the hazard function of a certain combination of exposure variable, which is different from this combination. This quotient keeps or yields the hazard rate ratio. So this ratio can be less than 1, equal 1, or greater 1. If the hazard rate ratio is equal 1, then both hazard functions are equal. That means there is no differences between these two groups constituting or based on the exposure variable. And that means that both groups have the same time to event experience. Because the hazard function is related to the survival function. And if the hazard functions are equal, then the survival function must be equal to 2. So that means if the hazard rate ratio is equal 1, that means the hazard function is equal. That means that the survival function is equal, so that both groups have the same time to event experience. If the hazard rate ratio is less than 1, then we have a decrease of the hazard function compared to the hazard function in the numerator. If the hazard rate ratio is greater than 1, then there is an increase of the hazard rate function compared to the hazard rate function in the numerator. That means that the group in the denominator has a worse experience, time to event experience, compared to the group which are in the numerator of the hazard rate ratio. I will explain it by the leukemia study, where we perform logistic Cox regression. And the Cox regression in this data can be done by using SDA-Cox. And here I would like to consider firstly only treatment. That is, we consider only treatment as an exposure variable and perform the Cox regression. Also, here you have some information concerning the estimation of the coefficient, so you can omit them. Then you have some information about the number of subjects in your data and how many events occurred or how many patients relapsed, and the sum of time at risk for all patients. And the interesting table is this one, where you get the hazard rate ratio for treatment compared to placebo group. Again, you have to initialize once that you work with time to event data using STSet or the STSet command in data. To get the Cox or Cox regression, you have to initialize STSet time to event data. The output for Cox regression you are interested in this table presented. Here you have the hazard rate ratio for the treatment, which is about 0.22. What does it mean? Here's the hazard rate ratio for the treatment. Is about 0.22. Having in mind how you labeled the treatment with 0 and 1, the hazard rate ratio is nothing else the ratio of the hazard in the treatment group divided by the hazard function in the placebo group. So the hazard rate ratio, which is presented here, is the ratio of two hazards. Dependent of your data coding, the ratio here in this case is the ratio of the hazard in the treatment group to the hazard of the placebo group. So this constitutes the hazard rate ratio, and in this case the hazard rate ratio is 0.22. That means we have a decrease of the hazard. That means the hazard in the treatment group to experience the event of interest, in this case to relapse, is less than the hazard in the placebo group. And you can say that is about a quarter. So the hazard in the treatment group is about 25% less compared to the hazard in the placebo group. So what can you deduce from this interpretation? That the hazard rate ratio is less than 1, or that the hazard in the treatment group to experience the event of interest is less than the hazard in the placebo group. That means that the treatment group has a better time to event experience compared to the placebo group. Okay.
Can you please repeat it one more time?
What?
The hazard to experience the event in the treatment group.
The hazard rate in the treatment group is about 25% the hazard in the placebo group.
The other way you say it.
That means that the time to event that the treatment group has a better that the treatment group have a better time to event experience compared to the placebo group in terms of survival probability. What you have seen in the Kaplan-Meier plot, where the survival probability or survival function in the treatment group was above the survival probability or survival function of the placebo group, because of the equivalence between hazard function and survival function. From the hazard function you can get some information concerning the survival function, vice versa. Or in other words, or loosely speaking, I wouldn't say it, that the treatment group, that there are more patients, it's loosely speaking, yes, that there are more patients in the treatment group remaining in remission compared to placebo group. So there is a treatment effect. So the treatment can reduce the occurrence of the event of interest or can reduce relapsing. Or can prolong prolongation, or can prolong to, or the treatment has the effect that the patients in the treatment group can be longer remain in remission compared to the placebo group. So if you incorporate a second exposure variable, which is in this case the logarithm of my blood count cells, we get this table where we have these two exposure variables, treatment and the logarithm of my blood count cells. And what you can see also, or what you can't see also from this output, there is no information concerning the baseline hazard. So we do not need the information concerning the baseline hazard. And here we only interested, or yes, here in this case we are only interested in the regression coefficients for the exposure variables and not on the baseline hazard. Here's the hazard rate ratio for the treatment group adjusted for the logarithm of white blood count cells. So the hazard rate ratio in the treatment group is about 2.27. And what you can deduce is that the treatment group has a better time to event experience compared to the placebo group, adjusted for the logarithm of white blood count cells. And it's almost the same as the interpretation here. The hazard in the treatment group is about 25% the hazard of the placebo group. Adjusted for the logarithm of white blood count cells. So again, you can say that the time to event experience in the treatment group due to a hazard ratio less than 1 is better compared to the placebo group in the sense of survival function or survival probability. So as I already said, that you can perform or can examine confounding or interaction as well in Cox regression. Here we can consider if the logarithm of white blood count cells is a confounder for the association of treatment of time to relapse. So here you have the hazard rate ratio for the logarithm of white blood count cells. And now, before I would answer this question, I would interpret this term or this value of about 5. That means that if you increase the logarithm of white blood count cells of 1 unit, then the hazard rate increases by a factor of 5, adjusted for treatment. That means adjusted for treatment in both groups, in the placebo group or in the treatment group. Increasing the logarithm of white blood count cells by 1 unit implies that the hazard rate increases by a factor of about 5. If the logarithm of white blood count cells is increased by 1 unit. The logarithm of white blood count cells increased by 1 means that you multiply white blood count cells with 10. So 10 times, or if you increase the logarithm of white blood count cells by 1, means that you multiply or that you increase the white blood count cells by a factor of 2. Take the logarithm of this product, then you can say that by increasing the logarithm or the white blood count cells by a factor of 10, then you would get an increase of the hazard ratio by a factor of 5, adjusted for treatment. So it remains to answer the question if the logarithm of white blood count cells is a confounder. So we have to compare this output with the former output, and we have to compare the hazard rate ratio, the coefficient. So what would you deduce? 0.22 compared to 0.27. Would there be a confounding?
Oh. It's not more than 10%.
So you have to calculate the relative difference of the hazard ratio, and you have a rule of thumb: if this relative difference is more than 10%, then you would expect there is confounding. It's 18%, okay. So you have a relative increase of the hazard rate ratio in the model without logarithm of white blood count cells, which is calculated with 0.22. So you have a relative increase of the hazard rate ratio of 18% to 0.27. So you would think that the logarithm of white blood count cells is a confounder. So what about interaction? Oh. Give me 5 minutes. Interaction can be answered in the same way. Here I would consider if the treatment interacts with the gender of the patients. That means, is the treatment effect on remission time different for men and women adjusted for the logarithm of white blood cells? I have to leave, or I have to change the logarithm of white blood cells in my model because the logarithm is a compounder. And to incorporate an interaction term between treatment and gender, I have to combine them with the star symbol and have to put the xi option before SD cost. And then I get this table, and before, or if I want to interpret or if I examine interaction, I have to look at this line where the interaction is presented and have to look if the interaction is significant. So I can deduce, or I would deduce that on the level of significance of 5%, that this value is less than 5%, and so there is a significant interaction between treatment and gender on the remission time. So I have to perform a stratified analysis, so I have to stratify concerning gender. First I have to, here this is the output for females, and here's the output for males for the Cox regression. And here you would see that in the group of females, the treatment effect is higher compared to the treatment effect in the group of males.
But it's not significant.
Here in this case it's insignificant. So we have a different time to event experience in the female group compared to the treatment to the male group with respect to the treatment. So women reacts different concerning the treatment compared to men, because there is no significant treatment effect in the female group compared to the treatment effect in the male group. There is a significant effect. So the effect of treatment in both groups, in females and males, are different. So here is a summary what to remember. Here are some literature, and last but not least, I would like to thank you very much for your attention. Wish you a nice time. Merry Christmas and Happy New Year.
That was great.